Hello, good evening, everyone. Hello, am I audible? Hello, 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 hello. Am I audible? Okay, cool. So I'll start the class. There's something attendance. So so to see. I'll take the attendance at the later in the class. So let me just introduce you with the course. As you all know, the course is like Electronic Theory of Solids, and it is 2025. You know that the course instructor is Professor Agya. He is from IIT Kharagpur, alumni of IC Bangalore. And let me introduce myself. I am Mohit, and I am a PMRF at IC Bangalore, doing PhD in physics in experimental condensed matter. And this course will be of level UG and PG that you guys know. I think since you have registered on this course, I'm just giving a quick briefing over it so that you guys know what it is. And second, just a minute. Right. And the start date of this course, just write these values. Is 20 Jan 25. This course will end on 11th April 25. So it will be a 4-month course. Exam registration dates is 14th Feb. This whosoever is will be writing this exam, crediting this course should note this down. This 14th Feb is the exam registration date, and exam will be on this date, which is 4th of May 2025. Now, for whom this course is, like what this course will take you, this course will take you here. So I'll just go over the course objective initially. So it is basically for the guy who are like have interest in the material research, the condensed matter, basic condensed matter, the magnetism, all those things. For those guys, it's interesting. So the course, as I could see from the whatever the syllabus is given, it will be having the foundation concepts on basically the elect. So this will be like the Drude theory, which treats system as the classical gas. And then things will go on building like advanced. In the advanced stages, it will be more like graphene, discussion on the graphene, which is a 2D material, and nanotubes. After that, the course will go in the direction of the magnetism. And you all know why the magnetism is important, because in the memory devices. So there'll be an introduction about the magnetism. Then it will cover the various the susceptibility, paramagnetism, ferromagnetism, all those things, the calculation, and the magnetic Hamiltonians. Then the course will go on seeing the superconductivity, which will be like the BCS theory, and maybe some application of superconductivity, which you all know, like ranging from MRI in condensed matter research, typically like superconducting magnets, which can give magnetic field of tens of Tesla. That's only possible because of the superconductivity. Then the physics will go towards the low dimensional systems like 1D, 2D, how the density of states will go. 1D, 2D, what is 1D, what is 2D, their definition, and the density of states, profile. These will be covered in the course. And then there will be spintronics and velitronics, which has to do with the spin and the value of the system. So that's the basic overview. In today's class, what I will be discussing is the assignment. I think you all know the week 0 assignment, assignment number 0. And these are the questions. Most probably you guys would have gone through the assignment. And in this particular class, I'll be solving each of these problems and describing what does, like how to solve the problem. And this is just a basic, it just requires the basic uh, fundamentals of the condensed matter and the quantum mechanics. So I'll be starting with the first question. The question which goes is which of the following is the effective mass if an energy wave vector relationship for a particle of mass m has the form E is equals to h bar square k square by 3m. So looking at the Hamiltonian itself, h bar k is, we know, k square by 3m. We know h bar k is what? P square by h bar k is, we denote P is h bar k equals to P. This implies P square by 3m. And we all know that, okay, for a classical particle, the free particle, energy is what? P square by 2m. If we compare these values, that P square by 3m, what you get is like effective mass, that is the m star here. 2m star is equals to 3m, and this will give you m star is equals to 3m by 2. So that's the very naive explanation of it. It's not very right. So I will derive the like how the effective mass is defined and how do we evaluate it. But this is how, if you compare this given dispersion relation, that is h bar square k square by 3m, just without taking any derivative, all those things, you can get to the answer. That answer is 3m by 2. But there is a more accurate and precise way to get the answers, because every time the relationship won't be like this. And for that, the effective mass, we have to understand the concept of the effective mass. That what do we mean by when we say that the effective mass? What does it mean? So when an electron moves in a lattice, its dispersion relation, it's the electron is not a free particle which can move like a free particle, the p square by 2m, but it gets attracted or repelled by the interactions, the ions, electrons, and all those information, the hopping parameters, all those things, they changes how the electron moves in the system. So if you now that changes the dispersion relation, but if you still want to apply single particle physics picture like that is an electron moving in a crystal, then you will have to define effective mass that okay this is the effective mass which incorporates all the interaction terms, and that is what the effective mass is. So it is a concept basically. It is a concept which is used in condensed matter and describes the response of the particle or the carrier, whatever the carrier it is, to external forces such as electric or magnetic field, how the carrier will behave in presence of electric or magnetic field. And it is defined in terms of the band curvature. And what does it accounts? It accounts for the interactions which I described, that there will be an interaction of the periodic potential. So it accounts for the periodic potential effects of material. How it is defined? Effective mass m star is defined as h bar square and then del 2E, that is energy, by del k square inverse. K is the momentum, E is energy, and K is wave vector, and h bar k is momentum. So m star goes as, now in our case, let's see what is E. E is defined in the question problem. It's given as E is h bar square k square by 3m. Now let's just substitute. This is equation 1. So del E by del k will give me 2h bar square k by 3m, and del 2E by del k square will give me 2h bar square by 3m. This is my equation 2. Substituting 2 in 1 gives me m star as h bar square times 3m by h bar square. This gives me 3m by 2, and that's the answer. So if you look in the option of it, so the correct answer is 3m by 2. If anyone has a doubt, they can raise the hand or ask it in the comment section. Comment section is open. I'm just continuously looking at the comment section. If anything comes, I'll definitely address it. If there is no doubt, then I'll move on to the problem number 2, which is what is the first excited state energy of a free electron in a one-dimensional. What is the first excited state energy of a free electron in a one-dimensional infinite potential well, whose width is a and vector is k is equals to 2 pi by lambda. So it is asking that there is an infinite well potential. The question is, there is a potential well which extends to infinity potential at the boundary. The width of this potential is a, And this is standard 1D box problem, which is the basic quantum mechanics. And we know that for such a well, the energy En is given as n square pi square h bar square by 2ma square. If this is not clear to anyone, I can explain this how it comes. Otherwise, if you guys know that where this relation comes from, I will continue from this point, this equation. This is particle in a 1D box. So let me just give it very briefly. So what actually happens is like this is a particle in a 1D box. So you take the Schrodinger equation h bar k square by like by okay. So you take the Schrodinger equation, and in that you apply the constraints that at boundaries psi of a will be 0. Psi of a at the boundaries, because the particle cannot escape from these points. The outside the probability of finding the particle is 0. So the ground state wave function will be like this, sine of kx. Then there will be first excited state whose wave function will be like this, because there has to be node at these ends. The particle cannot exist outside it, and the wave function has to go to 0 at this point. The probability of finding the particle outside the box is 0. That's why this will be the first excited state. And for these systems, if you evaluate the energy, it will turn out to be n square pi square h square by 2m square, where n will go from n is an integer and starts from 1 to n z plus. So it's a positive integer and goes from 1 to 3 like this. For 1, n is equals to 1, E1 will be given as pi square h bar square by 2m square, and this is known as the ground state energy. This is the minimum energy which a particle can attain in this system. Now, for first excited state, E2 will be given as 2 square pi square h bar square by 2ma square. This will be 2 pi square h bar square by ma square. Here, I think you know, okay, let's not assume you know all the symbols. So E is energy, pi is 22 by 7, h bar is Planck constant, h by 2 pi, and its value h is 6.626 into 10 power minus 34 joules second, and A is the width of the potential valve. Now, if I draw the energy spectrum, minimum energy that is possible E ground or E1 is pi square h bar square by 2ma square. So if I on y-axis, if I draw the energies. So this is my energy axis. So my ground state energy will be, this one will be pi square h bar square by 2 ma square. The next one will be, this is for n is equals to 1, then there will be n equal to 2, that energy will be 2 pi square h bar square by ma square. Now similarly n is equals to 3, and that will be 9 pi square h bar square by 2 ma square. And that it will keep going on. Now let's see what the question asks. The question asks is, what is the first excited state? First excited state is, ground state is the ground state, and after that there will be first excited state. The next energy will be second excited state. The third energy will be the third excited state. So the first excited state means n is equals to 2. So this is ground, this is first excited, this is second excited. So the first excited state, it will be E is equals to 2 pi square h bar square by ma square. And here in this given options, the E2 is the answer, 2 h bar square pi square by ma square. So this is one way of deriving it. Other ways, since I told you that this is like, it's a potential well. Inside the potential is 0. Inside this well, potential is V is 0. Outside V is infinite. Outside V is infinite. So this wave function which will come out will be of form sine kx. Actually, it will be sine nkx. Sine n pi by L, right? And then you take the energy as, the k here will be n times k, and then h bar square k square by 2m. So that will be n square pi square h bar square by 2m square. That's how it will come out. You want to derive it, it will be like this one only. So there can be different ways in which this relation can be derived actually. I'm just telling one or two ways, but there is more to it. Now, if you have any question or doubt, you can ask in this question. Then only I will move to the next one. Okay, if there is no question, then I'll move to the next question, which is next problem, which is like, graphite is a good conductor of electricity due to the presence of, the options are either lone pair of electrons, free valence electron, cations, and anions. So let's understand first the structure of the graphite, how the graphite is made. So graphite is made up of 2D layers of 2D layers of graphene. So if we understand the graphene, then we understand the graphite, because then they are like the vertically stacked. So how the graphene structure is, it is like famous honeycomb lattice. Let's make it. Then it goes like, and each of these points which I am drawing, these blue points, They are carbon, whatever I have drawn these, and they are the bonds, covalent bonds. So if you see, for example, this carbon, 1 second. If you see this carbon, then it is attached to one this carbon, one here and one here, right? And we know that the carbon has the four valence electron. Now we are bonded. We are bonded here. One is here, another is here, another is here. So three bonds are there. Now one valence electron is free. And that electron, those electrons, so there will be many of these attached to each carbon atom, those free electrons. And those three electrons conducts the electricity in graphite, in graphene. And since graphite is just like layers, is made up of layers of graphene. This implies that in graphite also p valence electron contributes to conduction. Let's rule out the other options also. So the first one is lone pair. Okay, so the answer is free valence electron. What is lone pair? It's a pair of electron. We know that's not a pair of electron. There is only one electron per carbon atom. So this rules out. There is nothing like charged particles here, like because graphite itself is a charged neutral, equal number of proton and the electrons. So there is nothing like cation or anions. It's just the free valence electron which is there in the graphite which conducts. And graphite is made up of, you all know that the pencil which we use, the core of it is made up of the graphite, and that is made up of the layers of the graphene, which can slide on top of each other. They are like not bonded, covalently bonded with each other. That's just the van der Waal attached. So that's why they can be exfoliated. And nowadays it's a big like research topic, the graphene. So people can actually exfoliate the graphene and can make it single sheet of atoms and can do the transport it and can verify all these details and have been verified. And my work is particularly on the graphene, the work which I do. So we thin down the graphite to single sheet of atoms and then we study the transport through it. So it's an ideal system to look for the transport in the system, that how the electron moves, and if one can twist the two layers of the graphene, one can see the superconductivity, Mott insulator, then the ferromagnetism, ferroelectricity, all those phases can be seen and have been seen in our group also and in the various group in the worldwide, and that's what we do. And the reason behind its core conductivity and all those fascinating property, is essentially lies in that there is a free electron corresponding to each carbon atom to which it conducts. Graphene itself is interesting. Just let me just graphene. This person is like h bar kvf. If you see it, it is like h bar k is momentum p, vf, and I can write it E is equals to ec, right? So it reminds you of the energy of a photon. E square is equal to P square C square with zero effective mass, and that's what the graphene is. So in graphene, the carriers has effective mass zero. So all the carriers move at a constant speed, unlike in the classical systems of the P square by 2m, where more the momentum, uh, like every particle moves with the different particle moves with different speeds. But in graphene, each particle moves with a one speed, that is Vf, and that is 10 power 6 meter per second, two order of magnitude less than the speed of the light. That's why it's important, and the experimental verification of those relativistic mechanics has been done in the case of the graphene, because it resembles the properties of the photon, that E is equals to Pc, and those studies has been done in the graphene. So that's it. If anyone has question, doubt, suggestion, they can ask in the comment section. Okay, well, if not, then I'll move on to the next question, which is, given the tight binding dispersion relation, some dispersion relation is given, E is equals to E naught plus A sine square K by 2, where E naught and A are constants, and A is a lattice parameter. So A has to do with the spacing of the lattice parameter. E naught and A are just a normalization constant, and they are asking that what is the group velocity of the electron. So, and they are also defined what the group velocity is. So Pg, that is the group velocity, it tells you about how the wave packet moves in the quantum mechanics, how the wave packet moves, the information moves basically from one place to another place, and at what speed. So it's a group velocity, and that's like 1 by h bar del E by del K. That's the definition of the group velocity. That's how it's been defined. Now, since everything is given, all you need is just the basic mathematics. Ek is E is a function of k, that is the wave vector. E naught is just a constant. A sine square ka by 2. So this is my equation number 1, and this is my given equation 2. All these are given in the question. All I need in this equation is take a derivative of E. So del E by del K is E naught is just a constant, so its derivative will be 0, plus A is a constant. Sine square we know, it will be 2 sine Ka by 2, and then derivative of sine will be cosine Ka by 2, and the derivative of Ka by 2 will be A by 2. So this boils down to del E by del K is A sine Ka by 2 cos Ka by 2 times A. So A comes in the front. So I think it's like A sine K by 2 cos K by 2. But nothing is like this in the options. The given options don't have the cosine. So we'll have to convert it to the form which resembles the given options. So what we'll do, we know that sine A cos B will be half of sine A plus B, or minus sine A minus B. If I'm not wrong, that's how it is with cos. You can check it. And it will be minus or plus. I think this is the right one. It will be sine A cos B plus cos A sine B. And then this term will be sine A cos B minus plus cos A sine B. I think it will be plus, and then this will be minus cos A sine B. So these terms cancel out, and sine A, and yeah. So this is the formula. So I can write this sine A cos B as sine A plus B, and plus sinus minus A minus B. So del E by del K goes as A times half Sine A plus B will be sine Ka, plus sine A minus B will be Ka minus, it will be 0, K by 2 minus K by 2. Sine 0 is 0. So del E by del K is Ka by 2 sine Ka, and we know that Vg is 1 by h bar del E by del K. So it will be A by 2 h bar sine Ka. Now let's look in the options. It will be A 2 h bar sine Ka. But what we have here is we don't have the h bar in this case. So all, if dimensionally, if you make it to correct, all the equations should have the h bar in the bottom. But sometimes what we do is we take h bar as 1. So in, like, basically in theoretical calculations, we take the h bar, it's just a constant, so they take the h bar is equals to 1. That makes the life easy. So if you take the h bar is equals to 1, then it gives you Vg is Aa by 2 sine Ka, and that matches your answer number 3. Option number 3, Vg is Aa by 2 sine Ka. And so if that's clear, then we can move on to the next answer. If you have a doubt, we can discuss it also. You all can ask if you have any question or doubt. You can always ask it in the comment section. Okay. If no question, then I'll move on to the next one, which is like, assuming that the conduction electrons in copper behaves as a classical gas, calculate the average value of the electron speed. So let's see what information do we have. So assumption, which the question only tells us to make that it's a classical gas. So that's the classical gas of electrons in copper. So we are assuming that they are classical particles, so they can collide with respect to each other. They don't have any interaction. They are like the ideal gas, which don't have any interaction. They can collide with each other, and all the properties of the classical gas directly implies here. They will be applicable. Then they also give the temperature of the gas. Temperature of electron gas is 300 Kelvin. That's what the question tells me. And now the question asks me, what is the average speed of electrons? So electrons are like nothing like but the classical gas particles. So whatever information I have from the classical gas picture, so that I can apply here. So we know the average speed they are asking, not the velocity. So speed we know it's just the modulus of the velocity, right? So you take a modulus of the velocity, integrate it with respect to the Boltzmann statistics, and you do the calculation, and what you get is in return. This is the standard result that V average is under root 8 kT by pi m, right? Where m is the effective mass. If that's the case, then here K is Boltzmann's constant. Average speed is V average. K is Boltzmann constant. T is temperature. Me is the effective mass, or let me write here the mass just because
and pi is nothing but 22 by 7, which you all know, the constant. So all we have to do is just a mathematics. So let me just do it for you guys. So V average is under root 8 times Boltzmann constant. We all know it's 1.38 into 10 power minus 23 joule per Kelvin, I think. Right. 1.38 into 10 power minus 23. Dimensions are right, I think. Kelvin, temperature is 300 Kelvin. By pi is 22 by 7. And mass of electron we all know 9.1 into 10 power minus 31 kg. So all we have to do is solve this V average. So it's like, let me solve the first term. Under the job 400 into 1.38. Let me just write it in under A by, and let me just calculate A and B separately. A is, just use a calculator. So if I use a calculator, and I can compute it here also. So it's 8 into 1.38. So it's 8 times 1.38 will be 11.04 times 300 will be 3.312 into 10 power minus 20. Right. Just a second. So it's like 8 8 times 1.38 times 300 will give me 3312. So 3312 times 10 power minus 23, that I can write as 3.312 into 10 power minus 20, and B I can write as 3.14 times 9.1, that will be 28.57 times 10 power minus 31, or 0.8586 roughly, to 10 power minus 30. So if I take V average, it will be 3.3 divided by 2.8 under root times 10 power 5 meter per second. So if I just do the simple calculation, 3.3 divided by 2.8, that will give me 1.17. Average is 1.17, 10 power 5 square root meter per second. And if I take square root of it, 1.178, that gives me roughly 1.08 into 10 power 5 meter per second. Now let's look the option. So the answer which we have got is like 1.0 into 10 power 5 meter per second. Here, let's look what is the closest one, because we have taken some approximation in the calculation. So if you look at the by the order of the magnitude is 1.6. The closest one is 1.2 into 10 power 5. So the C is the right answer for that. And now let's move to the question number 6. If you guys don't have if you have question or doubt, you can always ask in the comment section. That's what I'll be looking to. Now moving to question number 6. The 6 is, to get a n-type semiconductor from silicon,
it should be doped with a substance with number of valence electron equals to. So let's first understand the two concepts. What is the n-type semiconductor? And the second one is silicon. So n-type semiconductor is the one which has electron-like carriers. Not hole-like carriers. It's electron-like carrier. It's a semiconductor which is electron doped, or better right. It's a semiconductor which is electron doped. Okay. Silicon, it's a semiconductor. I think with a band gap of 0.7 eV, if I am not wrong, roughly of this order. And if you understand the silicon, how the silicon is, so it has 4 valence electron, and it makes the bonds like this with the silicon. So all the 4 bands are like occupied for it. Like this, so it will be like here also the silicon, and this one continues on both sides. So if you want to make it an N type, you will have to dope it, right? You will have to replace one of the silicon with some other element, and that element has to be such that X, let's say that the sub element doped. So to it should have, for electron like doped, it should have at least more than 4, right, valence electron. Why? Because one of its valence electron will go in making bond with silicon here, 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 here. So if the 4 are there, then it's like a silicon. It won't be doped. And if it is less than 4, it will be like a hold. So it will be a p-type semiconductor. But if you want to make it a n-type semiconductor, you dope it with a element which is like, which has the 5 valence electrons, so that one of the valence electron is free and that can conduct in the system. And that's what electron-like system is. Right. So, so to make it n-doped, substitute with a element with valency, with valence number or valence electron, with number of electrons greater than 4. In this case, option is 5, because all others 1, 2, and 3 will give you p type, not n type. So it will be, the answer is 5. Now, if you have any question or doubt, you can ask. Hey, SK, your camera is on. Will you please turn it off? Or if you have any question you're asking, you can just ask. Yeah. Now,
the next question which is there is like the potential of a diatomic molecule as a function of a distance r between the atoms is given as b of r minus a by r6 plus b by r12. The value of the potential at equilibrium separation between the atoms is, that's the question which we are asking. So I don't know whether you are familiar with this uh, potential or not, but this potential has a name, and it's a famous potential which describes the interaction between the particles, and it is known as the Lennard-Jones potential. Lennard-Jones potential describes the van der Waals forces. So VR is minus A by R6 plus B by R12. And this is the same potential on which I don't know whether you guys know or not, but this is the same potential on which the AFM works. AFM works. So AFM is atomic force microscope. So it has two terms. Because see, the answer I can derive it in like also you guys can also derive it in within a few fraction of seconds. But the motto of this question is not about just I think just deriving the equilibrium separation distance. It's more about knowing that what kind of potential it is, and there are two terms. One is negative, and the other is the positive. Here, not in this question, but generally A and B both are greater than 0. So let me draw the profile of this potential. So in the lobby. Yeah. So let me just draw the profile of this Lennard-Jones potential. So this is V of R. What will be the value of V, and this axis is R. Basically, the separation between the two these molecules, you can say. So if R is very large, R is very large compared to, of course, A and B. That's what you can compare because you can't call something large. So I cannot say 10 power 6 is a very large number. If I compare it with 10 power 23, then it becomes very small. But if I compare it with 0, then it's very large. So large and small, whenever we say, it has to be defined with something, with respect to something. So this is R. So R very large. Just a second. Hello. Hey, Professor Mahimanta. Yeah, अभी अभी मेरा क्लास है एनपीटीएल का, मैं आपको देर में कॉल करूँ. ओके. So if R is very large compared to A and B, then you see this potential dies because the denominator terms dominates. So the potential will be 0. It will be close to 0. So I'll assume it to be 0 in the point. Then if you come close, so there are two terms, r to the power 6 and r to the power 12 basically. So initially there will be attraction. So the negative terms will dominate. So there will be an attraction regime. So that's how it will go. And then there will be a repulsive regime if the particle comes too close. Then the second term starts dominating. So there is a point
here, where the derivative of it, let me call it Rm, where the derivative of this Lennard-Jones potential is zero, and this is the point where where the attractive and the repulsive force are both equilibrated, and that's the position. Because if you go from slightly move away from this point, for example, this point, if you are here, then it's an attractive potential, right? But if you are here, then it's a repulsive potential. If you are here, for example, then it's a repulsive potential. So this is the point where the attractive potential and the repulsive potential basically counter each other, and this is the point of the equilibration. And we'll be deriving the same point, the position of this Rm. So now coming to the question, the value of the potential at equilibrium separation between the atoms. Before that, I just want to tell you guys one more thing, that the AFM tips. So how do the AFM works? AFM working based on Lennard-Jones potential. So you have AFM cantilever, right? It's a flexible cantilever, and you take it near to the substrate, which has some structure like this. When it comes in contact, it's like you can think like the two particles whose potential is defined by the same, minus a by r6 plus b by r12. So when it's far away in this regime, it's an attractive potential. So it comes close to the substrate which you want to measure. But if you come too close, then it becomes repulsive. So the cantilever bends for attractive regime. It won't touch if you don't want it in the contact mode. For attractive regime, the your cantilever will bend slightly toward inside, so the attraction. For repulsive, if it comes too close, then it will become, this is for the repulsive. And then on the top there are laser spots on basis of which you determine the position. And with this one, with this AFM technique, one can measure up to few nanometer, 0.5 nanometer, like 0.1 nanometer, zero point 0.5. Oh, let me write very like normal number which we measure, which is the 1 nanometer. In our experiments, when we fabricate the devices using the same technique of the Lennard-Jones potential and all those things which are there inbuilt in the software, we can measure up to the difference of 1 nanometer. So 1 nanometer is something which you can't see by eyes, naked eyes, but based on this simple Lennard-Jones potential calculation and all those things, one can determine the height of the features which are of the nanometer size. Now coming to the derivation of this point Rm, the equilibration point. So V of R is minus A by R6 plus B by R12. We know force is what? Minus dV by dr. At equilibrium, force on a particle has to be zero. This implies that dV by dr will also be zero. So if I take this equation as 1, this is my 2 for equilibrium. So minus 6a by r to the power 7 if I take the derivative. So minus was plus, and then minus 12b by r13 is equals to 0. If I compute, I think that's what it will be, and then 6 so a by r7 minus 2b by r13 is 0. So r also goes. So this r, let me call it rm.
Rm is equals to 2b by a, and Rm is 5. Right, and this gives me Rm5 is equals to 2b by a. I think that's what it 7. This will be 6. So my Rm will be 2b by a times 1 by 6th. Now the question is the value of the potential. So now the problem is we have found the Rm. So let me just substitute the Rm there. So V of Rm will be minus a by Rm to the power 6 plus b by Rm to the power 12. Let's substitute V of Rm is equals to minus a by Rm is what? 2b by a to the power 6 cancels, and then b by Rm is what? 2b by a to the power 2. So V of Rm is minus a square by 2b plus a square by 4b. This gives me a square by 4b and minus a square by 4b. So V of Rm is minus a square by 4b, and that's the minimum VRM that's possible. So if I draw here, so this value, it is this value minus a square by 4b. That's what it means, V of Rm. So let's look into the options which are there. So the option number 3 is there, minus a square by 4b. If that's clear, if anyone has doubt, they can ask, else we'll move on. Now the next question is the percentage of an empty space in a body centered cubic arrangement is. So they are asking in a BCC structure, right? What is the percentage of the empty space? Yeah. So we know the BCC structure, right? Body centered cubic. It's known as BCC. So if I draw a cube kind of thing, so we all know that it has like these atoms which are there on the corner. And let me just draw a bigger one which is there at the center of the different color so that you can see it. They are of the same size. The radii is same. This is R, this is also R, this is also R, and this is also R. And the side of this cube is A. Then you can see this R, 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 R. That is the 4R will be root 3 times A, right? So the space occupied by these and effective number of these, because this point which is there, this corner, it is shared between 8. So one cube will be here. Let me just show you. One cube will come here, one on this side, one on this side, and then the 4 on the top. So it is shared between 8. So if you ask what is the what do we say? Uh, Basically, volume of the atoms, like how many effective number of atoms are there? There are two atoms, right, in BCC. One is this one, and another is
like 8 times 1 by 8. Effective number of atoms is 8 times 1 by 8 plus the central one, which is not shared. So the effective number is 2. So space occupied by atoms is what? 2 times the volume of a basically sphere is 4 by 3 pi r cube. So this goes as 8 pi r cube by 3. This is equation 1, right? And then I can take the volume of cube, that is a cube. So if I say that, okay, what is the fraction of the space which is occupied? So fraction of space occupied, or the packing efficiency, that's what we call generally packing efficiency, will be space occupied by atoms by space available. Space available. And how much space is available in that cube? So 8 pi r cube by 3 divided by a cube, that's the space available. This is packing efficiency. And if you recall, this one is equation 1. This is my equation 2. This is my equation 3. So substitute 1 in 3. So packing efficiency is how much? 8 pi r cube by 3 times a. I can write 4r by root 3 cube, right? And then this will be 8 pi by 3 times 4 times and then divided by 3 times root 3. If you solve it, it will turn out to be, we all know the standard number, it is 68%. It will be 0.68, and packing efficiency we multiply it by 100. So we will multiply by 100, so it will be 68%. If you solve this, it's simple if you do the mathematics here. And this is the packing efficiency. The question which has been asked is, what is the percentage of the empty space? Percentage of empty space is equals to 100 minus packing efficiency. It is asking how much space is available, empty space. So that will be 100 minus 68, and that is 32 basically. And if there is an option, so yes, they are asking it in percentage, so it is a percentage. And the correct answer here is 32%. Right. Now, the next question is, what is the coordination number in a square closed packed structure in a 2-dimension? So before that, first we have to understand what is a coordination number. Then only we will be able to address it. We will break the problem in 2 parts, and then automatically the answer will come out. So the first question is, what is coordination number? So it is the number nearest surrounding, is the number of basically nearest neighbors surrounding an atom, or it can be an entity. So it is the nearest number of the nearest neighbor's atoms, but number of the it is the number how many numbers of the nearest neighbor which are there to that whatever the atom or entity it is. So now this is the first part. The second part is they are asking the square closed pack structure. Square closed pack structure. I see. So let me draw it, then you will understand. So let me just draw a square closed pack structure. Now, since it is like a crystal or a lattice, so it can be translated infinite to the infinity. So I'll just translate it. And so on, it extends to infinity. That's how it goes. Now, these are my atoms. In a square lattice, the atom sits at the corner, right? So it's a square lattice whose unit cell you can describe like this is the unit cell, or you can say this is the unit cell. Any one box you can choose, and since it's a square lattice, so its x and y will be same. So if this is a, this will also be a. That's what it means when it's square lattice. Now let's combine these two and address the question. And question is what is the coordination number in a square closed pack structure in 2D? 2D we have drawn. Coordination number we know that it's the nearest neighbor. Nearest. You have to focus on the nearest neighbor. So this is my atom, for example. Let's look its nearest neighbor. The one nearest neighbor is this one, right? Which is distance A. Another is also this is A. This is also A. This is also A. Is this also the nearest neighbor? No, because this is root 2A. So this is not the nearest neighbor. This is the second nearest neighbor. Nearest neighbor are only these four, which are at a distance A, and A. So there are four nearest neighbor, and that's what the coordination number is. So the coordination answer to this problem is given as what is the coordination number in a square closed pack structure in 2D? That is 4. Okay. Anyone has any question, doubt, they can ask. Yeah. If no such question, then I'll move on to the final and the last question, which is like, which of the following statement is not true? So the first statement is paramagnetic substances are weakly attracted by magnetic field. So first we have to understand what is a paramagnetic substance. And then we'll be able to answer whether it's weakly attracted by magnetic field or it is not attracted by the magnetic field. So in a paramagnetic substance, there are unpaired electrons. It has unpaired electron. Since they are there,
they have their own angular momentum, right, which we call the spins. Spin is an angular quantum number, right? We all know from the quantum mechanics. Okay, so they are unpaired electron. They have their own angular momentum. So when they are brought close to the magnetic field, what happens? Spin align themselves in presence of the magnetic field such that they minimize their energy and they get attracted by the magnetic field. So the option number one rules out because this is a true statement. The paramagnetic substances are weakly attracted by magnetic field. So this is a true statement. Okay. Now, ferromagnetic substance cannot be magnetized permanently. This statement itself, we know that it's not true, and I explain why the answer is like that. So the ferromagnetic substance, we all know the ferromagnets, they are the magnetic material. So they do have the magnetic field inbuilt. And if they have the inbuilt magnetic field, then that means they are magnetizable and they can be magnetized permanently. And the reason lies that they have permanent magnetic movement. Basically, the spins are aligned automatically in a particular way to minimize their energy. So they have permanent magnetic moment, and which can align in the absence of external field. External field means the magnetic field. And we have studied it in our schools also, that the ferromagnets, if you take a ferromagnet, right, they have the hysteresis with the magnetic field, the properties, right? We know it from the class, I think 10th or 12th, that the ferromagnetism has the gives the hysteresis because the spins are aligned in a one direction. So when you apply a magnetic field, they get aligned in the direction of the magnetic field. Now when you change the direction of the fields and start changing, going to the negative field, what happens? There will be a resistance of the spin, and they will require a threshold magnetic field to flip, and that's give rise to hysteresis in the magnetic field for the ferromagnet. That itself tells that they can be permanently magnetized. So if I plot the flux density versus the magnetizing force, which is nothing but directly proportional to the magnetic field. This is P and this is minus P. Then we know that the curve for it, that the cohesive curve, there will be retentivity, then it will go like this, and then we all know that this famous curve for the ferromagnets, right? This is saturation corresponding to B negative. This is this point. This is saturation corresponding to, these are the saturation points. Similarly here also, then at these points there will be a finite, for example at this point, right, there is B equals to 0, but if you are moving in this direction, depending if you are moving in this direction or this direction, there will be a flux density, there will be some flux density at these points, and that's the permanent magnetization in the system. So ferromagnetic substance do have a like magnetization and which can be permanent. So this is false. This is true. Now let's see if it can have the multiple answers. The domain in antiferromagnetic substance are oppositely oriented with respect to each other. Yes, this is right. What is antiferromagnet? Antiferromagnet. From the name itself, you know that in the ferromagnet the spins are like of one directions only. This is ferromagnet, right? In antiferromagnet, one spin is like this, another is like this, up down, up down. So the net magnetic moment is zero. Of system is zero. That's why the domain the antiferromagnetic substance are oppositely oriented with respect to each other. Yes, this is right, and that's why antiferromagnetic substance do have the net magnetic moment zero. This is also true. Now coming to the final part, the pair of electrons cancel their magnetic moment in a diamagnetic substance. Yes, this is right. So electrons have their own magnetic moment, and in diamagnetic substance, like in which repel the applied magnetic field. So the magnetic moment of the electrons they cancel each other. There will be a pairing of these in the diamagnetism, and that's what the definition of the diamagnetism actually. So this is also true. So the answer corresponding to it goes like second, the second. So this is the correct answer, B. So that's what it is. I think 10 questions were there, and the first assignment uh, will be due on. I think you have the dates. You can check. 2nd Feb, I think. So just a quick recap. The first question was on the effective mass calculations. The effective mass is defined as m star equals to h bar d2 e by dk square inverse, where E is energy, K is wave vector, M star is effective mass, H bar is Planck constant. We take the double derivative of it and it gives effective mass. Effective mass itself means that when electron moves in a periodic lattice, it's like there will be like hopping parameter, all those things they get included in the dispersion relation. And if you want to treat it as a single particle, you change its mass and call the new effective mass, which is defined by the curvature of the band, that's the M star. Then you can apply all the basic single electron theory physics there. So this was single electron theory. The second question which we cover is what the first excited state energy of a free electron in a one-dimensional infinite potential well. So it's an infinite potential well which has V is equals to 0 inside, V infinite outside. The particle cannot reside outside because V infinity is there, so and the wall is there, so that it cannot jump. Probability of being outside is 0. Yeah. Here the ground wave function will be like this. The second excited state, the first excited state will be like this. The second will be like this, and that's how it will go. Energy will be given as n square pi square h square by 2 m square. For the first excited state, it will be above the ground state. The energy next to the ground state, that is the first excited state, that corresponds to n is equals to 2. So it is 2 pi square h bar square by 2 m square. And the third question, the correct answer for this one is turns out to be 2 pi square h square by 2 ma square. Third question was graphite is a good conductor of electricity due to the presence of. We discussed that okay, this is the structure of the graphene where it's bonded with the three atoms. So the carbon, one is free, one electron is free, and thus but that one valence electron conducts, and that is the free valence electron which is responsible for the conduction of the electricity in graphite. And since graphite is made up of graphene, that's what the process. Then I also discussed the importance of the graphene, which is a hot topic in condensed matter research, being it in MIT, Berkeley. In the MIT, there is a Pablo Zarello group who is doing this graphene, and in Berkeley there is Andre Young. Then in Harvard, Flip-Kim groups. So they are the famous groups which are doing research on the graphene, and it's turning out to be a very promising system. The next question, which was discussed, is how to calculate the group velocity for the given dispersion relation, and it's also defined how the group velocity is defined: 1 by h by del e by del k. You take the derivative, just do the mathematics, and you get the answer. Next questions was, if in a copper where you take the system to be like classical gas with no interactions, just a simple classical gas, Boltzmann statistics is applicable there. You just calculate the V average, which is like under root 8 kt by pi me, and that gives the number of 1.025, where k is Boltzmann constant, T is temperature, m is mass, and pi is 22 by 7. Now, next question was, silicon was there, and you had to make it the silicon n-doped. So you have to dope it with some impurity, and impurity valency has to be larger than 4 to make it n-dope. That's what we discussed, because one free electron you need to conduct, like like n-type, otherwise it would be a p-type if you make 3 valency. So the correct only option is 1. This is 5 valence you need at least to make it a n-type. Then we discussed the Lennard-Jones potential. In the Lennard-Jones potential, we had this diatomic molecule whose potential is given by this relation. And the question asks, what will be the potential at the equilibration separation between the atoms? So this is V of R as a function of R. R is the intermolecular separation distance. We see that at very large R, the interaction between the two particles is not there. That's why the V is 0. Once they starts approaching close to each other, there will be an interacting force. So with attracting force, which will be the first term minus A by R6, then it comes down, then B by R12 starts dominating at smaller r and shoots up. At this point is known as the equilibration point, where the force on the particle is 0 because the attracting and the repulsive potential are same. So this can be obtained by the derivative of V of R to be 0, where the force will be 0, and then you substitute the value of the Rm, the equilibration point, and what you get is minus A square by 4b, the potential value at that point. Then the question number 8, we discussed what is the percentage of empty space in a BCC structure. We draw the BCC structure first. This is 4R, and the cube volume is A cube. The effective number of atoms in the BCC is 2. One is this one, and 1 by 8 of such atoms. These are 8. So 8 times 1 by 8 is 1. 1 plus 1 is 2. And that's what we get. So, and then when we derive the packing efficiency, space occupied by atoms by space available, 8 by root cube, and then for percentage of empty space, we do it 100 minus packing efficiency. That gives me 32%, and that's it. This option number 3. Then what is the coordination number is square closed pack structure in a 2D. So we know the coordination number is the nearest neighbors surrounding minor atoms. So this is a square lattice which has these 4 atoms nearest neighbor. So the correct answer is 4, option number 3. Then the last one, the paramagnetic substances are weakly attracted by magnetic field. That's true, but we discussed that they have the unpaired electrons which can align with the external magnetic field, and that gives rise to the paramagnetism thing. In the ferromagnetism, they already are aligned, so they are ferromagnet, and at B equal to 0 also, they can have a inbuilt magnetic field, and that's why the magnetization. So the option number 2 is false, whatever is written, that they cannot be magnetized. Yes, they can be magnetized. That's the right. And then the third one is the domain is antiferromagnetic substances are oppositely oriented. Yes, in antiferromagnet, they are oppositely oriented. That's why the negative magnetic moment of this antiferromagnet is 0. Then the pairing of electron cancel their magnetic moment in a diamagnetic substance. Yes, that's true. In a diamagnetic, the pairing of the electron is such that they cancel the total magnetic moment, and that turns out to be 0. And this is also true. So the answer turns out to be the B, which is the ferromagnetic substance cannot be magnetized permanently. With this, I will conclude. And if you guys have any question, answers, suggestion, you can write in the comment box. I think I have to take the Attendance also, maybe somewhere, some around. At some point, there was some seat which was showing up in the chat box. Yeah, so here is attendance. Okay, attendance will come up whenever I leave. So I'll just take a screenshot of it so that I know who all are there. Guess I don't know whether I don't want to miss it. Yeah. If you guys have any questions, suggestions, answers, or whatever the questions you have, you can write in the comment box or you can ask directly. I'm here to answer. Those who join later, let me introduce myself. I am Mohit. I am a PMRF research scholar at Indian Institute of Science, Bengaluru. I work in experimental condensed matter, particularly in the graphene HBN moire, where we change the periodicity in the systems and then we study the physics of it, how the electron moves, and we do see the phenomena like superconductivity, which cannot be explained by the BCS theory. And these are the things which we work on. I'll be doing this TF for this course, the whole, the, it will be a 12-week course, I think. So if you have a question or answer, you can ask. Otherwise, I think it's a good time to see you guys. If you don't have any question or answer, maybe you can leave the meeting. Yeah. What are the attendance? Okay, then I'll stop the recording.